Hi, my name is Tanner Stevenson, and I'm a third-year graduate student studying neuroscience at UC Davis. I came to neuroscience through my undergraduate degree in biomedical engineering, where I initially wanted to work on medical devices that interact with our brain. However, after graduating and working at a startup that was developing a transcranial magnetic stimulation device to treat depression, I realized that what ultimately drew me to the brain was wanting to understand how the neural activity in our brain underlies our thoughts and behaviors, and how this activity can be disrupted in mental disorders. So my research is aimed at understanding the neural mechanisms that underlie our ability to behave flexibly in an ever-changing environment. For example, when we're driving a car and approaching a stoplight, if the stoplight turns yellow, we can do one of two things. We can either maintain our current behavior and speed up to make the light, or we can change our behavior and slow down to a stop. And we can make this decision in a split second. Importantly, this capability is impaired in mental disorders such as schizophrenia and obsessive compulsive disorder. So I want to know how a typical brain allows for behavioral flexibility so that we can better understand what may be going wrong in such disorders. Previous work suggests that dopamine plays an important role in behavioral flexibility by allowing the circuits that encode our behaviors and their neural activity to become more or less susceptible to updating the information that they encode. However, this relationship has never been directly proven. To address this gap in knowledge, I have developed a new behavioral task using rats that requires them to selectively maintain or update the information required to make a decision. In this task, the rats will hear either one or two tones of either a high or low pitch, and depending on the response rule, they will have to respond with a left or right poke based on the pitch of the relevant tone. In the first response rule variant, the first tone is the relevant tone, which requires the rats to maintain their upcoming choice in the face of a distractor tone. Whereas in the second variant, the last tone is relevant, and because the number of tones is variable, they must update their choice if they hear a second tone that is different than the first. With this task in place, I will then directly measure the difference in dopamine release between the two task variants using the state-of-the-art genetically encoded fluorescent dopamine sensor. If dopamine is in fact plays a role in flexibly updating or maintaining information in mind, I expect to see differences in dopamine release between the two task variants. If I do see such differences, I will then probe whether dopamine is causally involved in updating and maintenance by optogenetically stimulating or silencing dopamine neurons at specific points in the trial and seeing the effects on their behavioral performance. The result of this work will be the first direct experimental validation of decades-old theories of dopamine's function and behavioral flexibility, and it is my hope that this will help reform our theories of how this flexibility can be compromised in mental disorders. And I just wanted to say thank you again to ARCS for the support that has allowed me to pursue this research independently. Thank you again.